Welcome to the Deep Dive, the show engineered to cut through the information overload. We try and give you the essential insights you need to be, well, truly well informed. We know your time is valuable, right? So our mission is really to provide that shortcut, maybe those organic aha moments that make complex topics just click into place. Today, we're taking a deep dive into something that's, I think, rapidly changing how data professionals approach machine learning, BigQuery ML. We'll be exploring how this powerful capability allows you to build, deploy, understand, and manage sophisticated machine learning models directly within Google's BigQuery. And the real game changer. You do it all using SQL, a language many of you are already, deeply familiar with.
That's exactly right. And our goal isn't just to walk you through features. It's really to distill the most important, sometimes less obvious nuggets of knowledge about BigQuery ML. We want to uncover some surprising capabilities and practical insights that let you efficiently and transparently extract meaningful predictions from your data, all while leveraging your existing skill set. It's really
Wow.
about bridging that gap between data and actionable intelligence. And you can do it all from the comfort of your SQL editor.
Okay, so let's kick things off with the fundamental premise. What exactly is BigQuery ML, and maybe why is it such a significant development? Why should people care?
Well, at its core, BigQuery ML represents a bit of a paradigm shift, really. It enables users, data analysts, SQL developers, to build and use machine learning models solely through regular SQL commands.
Just SQL, no Python, no R.
Exactly. So if you're comfortable with SQL for data manipulation and analysis, which many people are, you're now inherently equipped to perform powerful predictive analytics, build recommendation systems, maybe even forecast future trends, all without needing to learn a new complex programming language or dive deep into specialized ML frameworks. Think of it like teaching your database to not just store and query data, but to actually learn from it and make predictions, using the very language you already speak.
Wow, that really is a profound simplification for, I imagine, a lot of data professionals out there. It really does sort of democratize machine learning, doesn't it?
Yeah.
Opens up these advanced predictive capabilities to a much broader audience who might not have that traditional data science background.
Precisely. It transforms BigQuery from, let's say, just a data warehouse into a powerful integrated ML platform.
Yeah, integrated is the key word there. Okay, so if BigQuery ML makes building models so accessible through SQL, what's the typical journey look like? Is there a kind of blueprint or a common workflow we follow when we want to get a model up and running?
There absolutely is. There's a structured life cycle, much like building anything complex. Let's say building a house. You start with the foundation, you move through construction, inspection, and finally, daily use. BigQuery ML simplifies these phases into a pretty clear step-by-step workflow, all managed through SQL.
Okay, let's walk through that, starting with the very first brick, maybe, which is creating the model.
Right. This is where you use the create model SQL command. It's the foundational step. It's where you tell BigQuery ML what kind of predictive task you're actually aiming for. Are you trying to predict numerical values like house prices? Or maybe categorize items like identifying fraudulent transactions? This command specifies the model's objective, its type, its initial architecture. You're basically laying down the blueprint for your predictive tool.
Got it. Blueprint established. So the next crucial step must be getting your data ready,
All right.
what we often call pre-processing.
Exactly. Before your model can learn effectively, your data needs to be clean, consistent, correctly formatted, all that good stuff. And what's particularly powerful about BigQuery ML here is its capacity for automatic data cleaning and feature engineering.
Automatic. So it does some of the heavy lifting for you.
It does. For instance, it can automatically handle missing values or maybe tidy up numerical inputs without you explicitly telling it to. But it also offers specialized functions if you need more granular control, if your data demands specific transformations. This whole phase is really like preparing the land and ensuring a solid foundation before you start building the house itself. You need that clean, stable base for reliable results.
Makes sense. So foundation is solid. Now we move to fine-tuning the model. You mentioned this is often called hyperparameter tuning.
Yes, hyperparameter tuning. This is a critical, often iterative process aimed at maximizing your model's accuracy and performance. Think of it less like just adjusting knobs and more like precisely calibrating the engine of your model to get the most efficient and powerful output. And the really neat thing is, BigQuery ML actually automates a significant portion of this for you. It intelligently searches for the optimal settings. We'll definitely delve into the nuances of this powerful automation a bit later because it's quite important.
Okay, looking forward to that. So once that engine is calibrated, how do we actually know if it's performing well? That's where we check how good it is, right? Or evaluate the model.
Precisely. Look, a model might perform perfectly on the data it learned from.
Yeah, the training data.
Right. But the real test, the acid test, is how it handles data it's never seen before. This evaluation step is absolutely essential for understanding your model's true real-world capabilities and ensuring it can generalize effectively. It's like doing a rigorous inspection of your newly built house, making sure it's sturdy, functional, and will stand up to real-world conditions before anyone moves in. This is another critical stage we'll definitely explore in more detail.
Okay, and then assuming it passes inspection, the exciting part, using the model to make predictions. This is inference, right?
Yes, inference.
Yeah.
This is the moment your model goes live, essentially, and starts delivering actual value. You feed it new data, and it provides an output, could be a prediction, a score, maybe a classification. So if you've built that model to estimate property values, you provide the details of a new house, and boom, it gives you an immediate price estimate. This is really analogous to moving into your completed house and enjoying all the benefits of your hard work. And we'll discuss the different ways BigQuery ML facilitates this practical application very shortly.
Okay, but sometimes the model gives you an answer and you're left scratching your head thinking, why did it reach that specific conclusion? That brings us to explainability.
Exactly right. Explainability, or XAI, is all about peering into that black box of machine learning. It helps us understand how each piece of input data, each feature, contributed to a particular prediction. It's absolutely crucial for building trust, for debugging, and for ensuring fairness in automated decisions. If your model predicts a certain outcome, you really want to know which features were the most influential in that decision. It's kind of like asking the architect why they chose specific materials or a particular layout for your house. You want the rationale behind the design, right?
Yeah, absolutely.
And BigQuery ML offers robust tools to uncover these insights, another capability we'll definitely delve deeper into.
Great. And then finally, for those who really want to get under the hood, you mentioned inspecting model weights.
Yes, this involves examining the learned internal parameters and structures of your model. It's about seeing precisely how different aspects of your input data are weighted or combined by the model to arrive at its predictions. It offers a really low-level view, much like examining the detailed blueprints and structural engineering plans of a house to understand every single beam and connection. This provides a deep understanding of your model's inner workings, which, again, we'll unpack further.
Okay, so it's really clear then. BigQuery ML isn't just like a single tool. It's a comprehensive suite. It equips you with a pretty versatile toolkit, allowing you to select the precise SQL function or approach needed for each stage of your machine learning journey, whether you're building, optimizing, deploying, or even just understanding.
That's the core idea, a full lifecycle managed within BigQuery using SQL, #Tech2, optimizing and validating your models.
Okay, so we've got that initial model built using the workflow, but how do we make it truly excel? How do we ensure it's not just functional, but actually optimal? This leads us right back to that crucial step you mentioned, hyperparameter tuning. And I like the analogy you hinted at. Maybe you think about perfecting a cookie recipe. You might have general ingredient ranges, right? But to bake that perfect cookie, the one everyone raves about, you need to find the exact right amount of sugar, the precise baking time.
That's a perfect analogy. In machine learning, hyperparameter tuning is precisely that critical process of fine-tuning your model's setting, its recipe, if you will, to achieve the best possible performance.
Right, so we're talking about settings the model doesn't learn itself during training. These are things we define beforehand.
Exactly. Hyperparameters are the architectural or configuration choices you make before the model even starts learning. They're different from the internal parameters the model discovers during its training process, like, say, the coefficients in a linear regression model. Hyperparameters are external. For example, in a neural network, the number of hidden layers or the learning rate, those are hyperparameters. Or for a k-means clustering model, it's the number of clusters you instruct it to find beforehand. These choices directly influence how the model learns and how well it generalizes.
Okay, but why bother tuning them? I mean, can't we just use the default values BigQuery provides, or maybe manually try a few different combinations?
Well, you could, but honestly, it would be incredibly inefficient and, most likely, suboptimal. Manually experimenting with different hyperparameter combinations is like trying I don't know, a million cookie recipes one by one.
Yeah, sounds exhausting.
It is. It's time-consuming, it's prone to human error, and you often miss the true optimal configuration. Hyperparameter tuning automates this entire search process within BigQuery ML. It intelligently searches for the best combination of these settings, saving you immense amounts of time and effort, and it helps ensure your model achieves its peak performance rather than just being, good enough. This automation is a really significant advantage.
That automation sounds incredibly powerful. So how does this actually work inside BigQuery ML? How do we tell it, okay, start tuning?
BigQuery ML integrates hyperparameter tuning directly into the create model statement itself. It's pretty neat. You simply add the num_trials option, specifying how many distinct batches or combinations of hyperparameters BigQuery ML should try out. So for example, mntrials 30 would instruct it to perform 30 different tuning experiments, trying 30 different recipes. And instead of providing just one fixed value for a hyperparameter you want to tune, you define a range or maybe a list of values for BigQuery ML to explore. So for continuous numerical values, like a learning rate, you use hparam range. You might specify something like learn rate equals hparam range 0.00011.0. That gives the system the freedom to explore any value within that continuous spectrum.
Okay, like finding the perfect sweetness level.
Exactly. And for specific discrete choices, like maybe trying different optimization algorithms, you use hparam candidates. For instance, optimizer hparam candidates, attagred, SGD, FTRL. That tells BigQuery ML to test each of those specific optimizers. This flexibility allows for a really thorough exploration of the hyperparameter space.
Okay, so beyond just setting these ranges or candidates, are there other sort of smart features or key things to consider in BigQuery ML's tuning process?
Oh, yes, absolutely. First, you specify your objectives.
Objectives.
Yeah. What specific performance metric should BigQuery ML aim to optimize? What defines a good outcome for your model? For regression models predicting numbers, you might target, say, mean squared error, MSE, aiming to minimize the average squared difference between predictions and actual values. For classification models, maybe RCSC is a common objective that measures the model's ability to distinguish between different classes. BigQuery ML's goal is then to find the hyperparameter combination that best optimizes this chosen objective metric. Second, and this is a crucial yet often overlooked benefit, BigQuery ML performs an automatic data split whenever tuning is enabled.
Ah, right. Splitting the data.
Yes, it rigorously divides your input data into 3 distinct sets. Typically, it's something like 80% for training data that's to teach the model, then maybe 10% for evaluation data, which is used during the tuning process itself to assess the different hyperparameter combinations. Think of this like tasting the cookie dough as you adjust ingredients.
Okay.
And the remaining 10% is set aside as test data. This test set is kept completely separate and is only used after all the tuning is complete. Its purpose is to provide a final, unbiased assessment of how the best found model performs. This isn't just convenient, it rigorously guards against a common and, frankly, insidious pitfall in ML data leakage between your training and validation sets. It ensures your model's reported performance isn't just an overestimation based on the tuning process.
Right, so it's proactively preventing you from accidentally cheating, essentially. Making sure the model truly generalizes to unseen data. That's a significant safeguard.
Precisely. Another aspect is the starting point for the tuning. If you don't specify a range for a hyperparameter, tuning begins from the model's default values. If your specified range includes the default, it starts there. Otherwise, it intelligently picks the closest value within your provided range as a starting point. It doesn't just start randomly. And then there's transfer learning, which is a really powerful, maybe less obvious capability.
Transfer learning in hyperparameter tuning. How does that work?
Well, if you've previously run hyperparameter tuning for similar model types within the same BigQuery project, BigQuery ML can actually learn from those past experiences. This allows it to find optimal hyperparameters for your new model much faster. It accelerates the tuning process, and it effectively avoids that cold start problem where the system starts completely blind each time. It's like having a seasoned baker who already knows good starting points for cookie ingredients based on, a lifetime of successful batches.
That could be a huge time and cost saver.
Yeah.
Leveraging prior work automatically. That's smart. Okay, speaking of cost, what are the implications there? You mentioned nm_trials.
Yes, cost is a factor. Each trial, each attempt with a specific hyperparameter combination incurs a cost. It's essentially for the computational resources used to train and evaluate that particular recipe. The total cost is simply the sum of all the trials you run. As a general guideline, maybe aiming for at least 10 trials per hyperparameter you're tuning is a good starting point. It gives the system sufficient room to explore. So if you're tuning, say, 3 hyperparameters, you might consider running at least 30 trials.
Okay, good rule of thumb. And what if?
Yeah.
What if after all this tuning, maybe running 30, 50 trials, the model doesn't show significant improvement? Does that mean something went wrong?
Not necessarily a problem with the tuning process itself, no. If the improvements are marginal, it could mean a few things. Perhaps the default hyperparameters were already pretty good for your data, and there just wasn't much room for improvement through tuning alone. That happens. More often, though, it's a signal that the bottleneck might lie elsewhere. You might need to explore entirely different types of models that are better suited for your specific data or problem. Or maybe more fundamentally, you need to improve your input data through better feature engineering or more robust data collection. Tuning showing little improvement often prompts you to reassess your overall approach, which is valuable in itself. Really, what's fascinating here is how hyperparameter tuning in BigQuery ML automates a critical, and let's be honest, often daunting part of machine learning development. It transforms what can be a tedious manual process into an intelligent, efficient search, making optimal model performance significantly more accessible and reliable, especially for data professionals working primarily in SQL.
Okay, so you've developed your model, you've precisely tuned it using that automated process. Should be pretty good now, right? But before you can confidently unleash it on real-world predictions, you need to rigorously assess its performance. This is where BigQuery ML model evaluation comes in. We could think of it as the model's taste test, maybe. You wouldn't serve cookies you haven't tasted to your guests, would you?
Exactly, spot on. Evaluation is absolutely indispensable. It allows you to understand the quality of your model. It lets you compare it objectively against other models you might have developed, maybe different tuning strategies or even different model types. And crucially, it helps you predict how well it will perform on new, unseen data out there in the real world. Without proper evaluation, you're basically operating on assumptions, not certainty, and that's risky.
So what are the core reasons this evaluation step is so critical for any serious machine learning project?
Well, there are 3 primary drivers, I'd say. First, just assessing quality. You need to quantify how well your model actually learned the patterns from your data and how accurately it can fit new observations it encounters. Second, comparing models. If you've experimented with different model architectures or maybe different tuning strategies, evaluation metrics provide that objective basis to determine which recipe is truly superior for your specific task. And third, predicting real-world performance. This is perhaps the most vital reason. Evaluation gives you a reliable estimate of how your model will behave once it's deployed, minimizing unpleasant surprises down the line.
You've emphasized the importance of using unseen data for evaluation. Can you elaborate a bit more on the distinction here, especially for supervised versus unsupervised learning models in BigQuery ML?
Yes, this is a really crucial differentiation. For supervised learning models, those are the ones that learn from data with known right answers, like historical house prices or maybe pre-labeled customer segments. The absolute gold standard is to rigorously test them on a data set they have never seen during the training phase. This is exactly why BigQuery ML automatically sets aside an evaluation set or a test set when you train, particularly if you enable that hyperparameter tuning we just discussed.
Right, to avoid that overfitting problem.
Precisely. You're probably familiar with overfitting. It's where a model essentially memorizes its training data too well, but then fails miserably when it tries to generalize to new real-world examples it hasn't seen. Testing on genuinely unseen data is the primary defense against this. It's like giving a student an exam on new material, not just the exact questions they crammed for the night before.
Good analogy.
So, for example, if you train a house price prediction model on historical San Francisco home sales data from, say, 2020, you then evaluate it on a separate, distinct set of San Francisco home sales data, maybe from 2021, that it didn't use for training at all. This ensures your model genuinely understands the underlying patterns, not just that it memorized the 2020 examples.
Okay, that makes sense for supervised. What about unsupervised models where there aren't really right answers?
Right. For unsupervised learning models, things like clustering customers into segments or reducing data dimensions with PCA, where the model discovers patterns or groupings in data without predefined right answers, evaluation is inherently, well, trickier. It's often more qualitative and complex. There are no straightforward accuracy metrics because there's no ground truth to compare against. Instead, you often rely on metrics that measure the quality of the clusters formed, like how tight or distinct they are, or maybe how much variance the model explains in the data. BigQuery ML still provides the ML evaluate function for these unsupervised models, but the interpretation of the resulting metrics is quite different. You're looking for different signals of success.
That distinction makes perfect sense. Okay, so practically speaking then, how does BigQuery ML actually help us perform these evaluations? What are the key SQL functions we'll be using day to day?
BigQuery ML provides several powerful SQL functions designed specifically to calculate these critical evaluation metrics. Your primary tool, the workhorse, is the ML evaluate function. Now, for prediction models, those are regression models predicting numerical values. You'll typically see metrics like mean, absolute error, MAE. This gives you the average magnitude of error in your predictions. So it might tell you, for example, that your house price predictions are typically off by about, say, $5,000. Then there's mean squared error, MSE. It's similar, but it heavily penalizes larger errors because it squares the difference, so it's more sensitive to outliers in your predictions. And the R2 score, or coefficient of determination. This indicates the proportion of the variance in the dependent variable, like house price, that is predictable from the independent variables, like square footage, bedrooms. A value closer to 1 signifies a better fit, meaning your model explains more of the variability.
Okay, that covers regression. What about classification models, the ones categorizing things?
Right. For classification models, ML Evaluate provides a really comprehensive suite of metrics that many people will be familiar with from basic statistics or data science courses. You get accuracy, which is simply the overall percentage of correct predictions. Then precision, which is the proportion of true positives among all the instances the model predicted as positive. So of all the emails flagged as spam, how many actually were spam? Then recall, which is the proportion of true positives among all the actual positive instances. So of all the emails that truly were spam, how many did the model correctly identify?
Right, the classic precision recall trade-off.
Exactly. And that leads to the F1 score, which is the harmonic mean of precision and recall. It offers a single metric to balance that trade-off, which is often very useful. Additionally, ML Evaluate provides ROC-AUC, Receiver Operating Characteristic Area under the curve. This assesses the model's overall ability to distinguish between the positive and negative classes across all thresholds. And finally, log loss, which quantifies the confidence of the model's predictions. Lower log loss generally indicates more confident and accurate probability estimates.
Wow, that's a pretty comprehensive set of metrics just from ML Evaluate. And for classification, isn't ML confusion matrix often cited as a way to get even more granular, to really understand the types of errors?
Oh, absolutely. The ML confusion matrix is invaluable for classification tasks because it breaks down the exact counts of correct and incorrect predictions into 4 categories. Let's use that email spam filter example again. A true positive, TP, is when the model correctly identifies an email as spam. It says spam, and it is spam. Success. A true negative, TN, is when the model correctly identifies an email as not spam. It says not spam and it isn't spam. Also success. A false positive, FP, this is a type I error, is when the model incorrectly flags a good email as spam. It says spam, but it isn't. It can be really annoying for users. And a false negative, FN, a type 2 error, is when the model misses a spam email. It says not spam, but it actually is spam. This means spam gets through to the inbox. This matrix provides crucial insights into what kind of errors your model is making, which is often more important than just the overall accuracy.
That breakdown is super helpful.
And one more for classification, specifically binary classification, the MLR-RCERVE function. This allows you to visualize your model's performance, the trade-off between the true positive rate and false positive rate across all possible classification thresholds. This helps you understand how changing the decision threshold, like how confident does the model need to be to call something spam, affects its performance, enabling you to choose the optimal threshold for your specific business needs. Maybe you care more about catching all spam, high recall, even if some good emails get flagged, lower precision, or vice versa.
Okay, so these evaluation metrics, are they automatically calculated when you first create the model? And crucially, can we run them again later, maybe on new data as it comes in?
Yes, to both. When you use Create Model, BigQuery ML typically performs an initial evaluation using that designated evaluation or test set we talked about. You can then easily retrieve these initial metrics by simply calling ml.evaluate directly on the trained model name. But crucially, yes, you absolutely can, and frankly, you should regularly feed your deployed models new unseen data and rerun ml.evaluate on that data. This is absolutely vital for ongoing performance monitoring. As real-world data inevitably evolves or drifts over time, your model's performance might degrade. Continuous evaluation helps you detect this degradation early, prompting necessary actions like retraining the model with fresh data or maybe revisiting the feature engineering. This really raises that important question, doesn't it? How do we truly know our machine learning models are fit for purpose and ready to deliver real value in a dynamic environment? Model evaluation is that indispensable step. It quantifies our confidence in the model's capabilities, highlights areas for improvement, and ensures we're not flying blind. It's the rigorous taste test before the product goes to market, and you keep taste testing it over time. Hashtag 3-3. Putting models to work and understanding them.
All right, so we've navigated the building, the tuning, the rigorous evaluation. Our model has passed the taste test. It's robust. It's ready. Now comes the moment of truth, right? Putting it to actual work. This is where model inference enters the picture. Sticking with our analogy, it's like having perfected that cookie recipe, and now you actually want to bake a whole batch for the big party. Time to produce.
That's a great way to put it. Model inference, which is also commonly referred to simply as prediction, is exactly that process. You take your trained machine learning model and you feed it new, unlabeled data it hasn't seen before, data without the answers, and you get an output, whether that's a prediction, like a house price, a score, like a customer churn probability, a classification, like spam or not spam, or maybe a recommendation. It's the point where your carefully crafted recipe goes from being a theoretical design to producing practical, hopefully delicious reality. And BigQuery ML provides several powerful avenues for performing inference, which we can broadly categorize into batch prediction and online prediction.
Okay, let's start with batch prediction. That sounds like the big party scenario. What's that involve, and how does BigQuery ML handle it?
Batch prediction is ideal when you have a large volume of new data that you want your model to process all at once, in one go. Think exactly like baking that massive quantity of cookies for a big event. You're generating many predictions in a single, efficient operation. BigQuery ML excels at this because of its inherently scalable architecture. It's built for large data sets. Now, first, for models that you've trained directly within BigQuery ML itself.
Our own recipes.
Exactly, your own recipes. You use the straightforward ML predict function. It's designed for this. So if you have that house price prediction model, you simply provide ML predict with a BigQuery table containing details of, say, 1 million new houses you want prices for. ML Predict will efficiently run the model on each row and typically append a new column to that table containing the predicted price for each house. It's super efficient. Similarly, for unsupervised models like that K-means model that segments customers, you give ML Predict a table of new customer data, and it will assign each new customer to their respective segment based on the patterns the model learned during training. It's applying your perfected cookie sorting logic to a massive pile of new ingredients all at once.
That makes perfect sense for models trained natively in BigQuery ML. But what if I've built a model using other machine learning tools, maybe TensorFlow or scikit-learn, outside of BigQuery ML? Can I still use BigQuery for prediction?
Ah, yes, that's a very common scenario, and BigQuery ML handles it beautifully. You can actually import models that were built in external tools like PyTorch, scikit-learn, TensorFlow, even XGBoost directly into BigQuery ML. Once you've imported that external model, you gain the significant benefit of BigQuery's immense processing power and, often, its cost efficiency for doing the inference step. You can then use the same ML predict function on these imported models just as you would with native BigQuery ML models. This lets you leverage BigQuery's speed to run predictions right where your vast datasets often already reside, which can be much more efficient than moving data around. It's like finding an amazing cookie recipe online from a famous chef, but choosing to use your highly efficient industrial-grade oven, which is BigQuery, to bake those cookies at scale.
Okay, that import capability sounds really useful. Now, what's the deal with remote models? That sounds like another layer of integration again.
Remote models are a powerful abstraction, yes. They're designed for scenarios involving very large, specialized, or perhaps compute-intensive models. These might be models that require dedicated hardware, like GPUs for inference, or models that are already managed and deployed within Google's broader AI platform, Vertex AI. So within BigQuery ML, you create something called a remote model, which essentially acts as a pointer or a reference to a model that's actually deployed over in Vertex AI.
So BigQuery talks to Vertex AI.
Exactly. When you call ML Predictee on one of these remote models in BigQuery, BigQuery seamlessly handles the communication. It sends your data over to the Vertex AI service for processing by the deployed model there, and then it brings the predictions back into your BigQuery environment. So, for example, if you have a massive, complex natural language processing model deployed on Vertex AI, you could leverage it directly from BigQuery ML to analyze terabytes of text data that resides in your BigQuery tables. It makes these advanced AI capabilities readily accessible from your familiar SQL interface. Using our analogy, it's like having a huge, complex catering order for thousands of very specific artisanal cookies. Your home oven, BigQuery ML alone, isn't quite enough. So you hire a professional bakery with specialized equipment that's Vertex AI to handle the specialized baking, but you still manage the order and receive the finished product from your BigQuery kitchen.
Okay, that covers batch prediction, processing big jobs.
Okay.
But what if you need a prediction right now, immediately, maybe for just a single data point, like one personalized cookie recommendation on demand for a customer browsing your website right now?
That's the domain of online prediction, sometimes called real-time prediction. Now, while BigQuery ML's ML Predictic excels at large batch operations, true real-time, low-latency needs for individual predictions are typically best served by integrating tightly with Vertex AI. Remember how we talked about registering BigQuery ML models in Vertex AI's model registry?
Yes.
Well, once a model is registered there, you can then deploy it as a Vertex AI endpoint. These endpoints are essentially always-on, highly available, scalable web services that are optimized for serving predictions with very low latency, often in milliseconds.
Ah, so it's a dedicated service just for quick predictions.
Precisely. A classic example is that e-commerce recommendation system. As soon as a user adds an item to their cart, you need instant recommendations for complementary products. Your website's backend would make a quick call to a Vertex AI endpoint, which is powered by your BigQuery ML trained model, to get those real-time suggestions immediately. It truly becomes like that cookie dispenser that bakes and serves one fresh, personalized cookie on demand instantly for every single user interaction. If we connect this to the bigger picture, model inference is fundamentally about translating those theoretical machine learning capabilities we built into practical, actionable insights that drive business value. Whether you're processing vast data sets in batches for strategic analysis or making instant decisions for individual customer interactions, BigQuery ML, especially with its seamless integration with Vertex AI, provides the flexibility and power to operationalize your models exactly how your business demands.
Okay, so we've talked about getting the predictions, the what. But often, the prediction itself isn't actually enough, is it? I mean, imagine your hypothetical self-driving car suddenly makes a sharp turn. You wouldn't just accept it. You desperately want to know why it did that right. Was it avoiding a pedestrian? Did it see a sudden obstacle? Or was it just a glitch? That crucial need to understand the why extends directly to our machine learning models, especially when they make important decisions.
Absolutely. And this is precisely where BigQuery Explainable AI, or XAI, becomes so indispensable. It's the set of tools and techniques designed to move models from being opaque black boxes to transparent, understandable decision makers. XAI provides insights into how each piece of input information, each feature in your data, contributed to a specific outcome or prediction made by the model. This concept is often called feature attribution. It's like getting a detailed breakdown, a receipt almost, showing exactly what influenced the model's final decision.
Beyond simply satisfying our curiosity, though, why is XAI so profoundly important in a real-world production environment? What are the tangible benefits?
Oh, XAI serves several absolutely critical functions. First and foremost, it fosters trust and verification. If a model makes a crucial decision, like approving or denying a loan application, XAI can help confirm that the decision was based on relevant logical factors like credit score or income and not on irrelevant or spurious ones, like, say, the applicant's favorite color. This validates the model's logical behavior and builds confidence among users and stakeholders. Second, it's an incredibly powerful tool for bias detection. XAI can reveal if a model is inadvertently relying on unfair, discriminatory features or perhaps proxies for them, like zip code potentially acting as a proxy for race. This allows you to identify and mitigate harmful biases before they cause real-world damage.
That's hugely important.
It is. Third, XAI is vital for model improvement. By understanding which features actually drive the predictions, you can make informed decisions to refine your model. Perhaps you need to collect more data for a feature that's influential but currently sparse in your dataset. Or maybe you can simplify the model by removing features that have very little impact. And fourth, in many regulated industries, think finance, healthcare regulatory compliance often mandates the ability to explain automated decisions. XAI helps organizations meet these requirements, making their AI systems auditable, accountable, and defensible.
Okay, so it's about trust, fairness, improvement, and compliance. Makes sense. Are there different ways BigQuery ML provides these explanations? Like, can it explain just one specific prediction versus explaining the model's overall behavior?
Yes, that's a key distinction. XAI typically offers two complementary perspectives: local explainability and global explainability. Local explainability focuses on the why for a specific prediction made for a single row of data. It's about dissecting an individual decision instance. So, for example, for a specific house predicted to be worth $500,000, local explainability might reveal something like, okay, the fact it has 4 bedrooms added plus $50,000 to the base price prediction, the large backyard added plus $25,000, but its older age subtracted negative $15,000, leading to the final $500K. In BigQuery ML, you typically use functions like ml.explainPredict for regression classification or ml.explainForecast for time series models to get this granular per prediction insight.
Okay, that's the why this one
Yeah.
explanation. What about the bigger picture?
Right, that's global explainability. This shows the overall influence of each feature on the model's predictions across the entire dataset. It provides a higher-level view of which features are generally the most important drivers for the model's logic. So for that same house price model, global explainability might tell you that overall square footage is the single most influential feature, followed perhaps by number of bedrooms, and then maybe location desirability index. BigQuery ML functions designed for global explainability include ML Global Explain, ML Feature Importance, which is particularly useful and intuitive for tree-based models, and ML Advanced Weights, which gives insights for linear models.
Got it. Local for specifics, global for the general trends.
Yeah.
How does BigQuery ML technically generate these explanations? Is it using specific algorithms under the hood to figure this out?
Yes, it leverages various well-established underlying techniques depending on the type of model being explained. For many model types, particularly tree-based and linear models, it often uses variations of Shapley values. These are rooted in cooperative game theory, believe it or not.
Game theory. Yeah.
Yeah. Shapley values effectively distribute the credit or payout for prediction fairly among all the input features, showing each feature's unique contribution to that specific outcome, considering all possible combinations of features. It's quite mathematically elegant. For neural networks, a technique called integrated gradients is often employed. This works by attributing the model's output back to its input features by examining the gradients along a path from some baseline input, like an all-zero input, to the actual input instance. And for forecasting models like our Mapless, BigQuery ML often uses time series decomposition. This inherently breaks down the forecast into understandable components like the underlying trend, seasonal patterns, and the impact of specific holidays or events, providing built-in explainability for the time series context. Now, it's worth noting again that while you can perform XAI directly within BigQuery ML using these powerful SQL functions, you also have the option, especially for models registered in Vertex AI, to leverage Vertex AI's broader and often more advanced XAI features. This can be particularly beneficial for complex models deployed for online, real-time predictions, where you might need deeper diagnostic capabilities or different visualization options. What's fascinating here, really, is that XAI is the crucial bridge. It transforms potentially opaque black box machine learning predictions into clear, understandable reasoning. This capability doesn't just satisfy curiosity, it makes your ML models more reliable, more responsible, and ultimately far more trustworthy and useful in critical real-world applications.
Okay, following up directly on explainability, what if we want to go even deeper? Beyond just understanding why a specific prediction was made, what if we want to understand how the model actually arrived at its internal logic? Think about our hypothetical robot flower identifier again. It correctly tells us a flower is a rose. XAI might tell us it focused on petal shape and color, but as a curious engineer, I might want to know more. What specific internal rules, what learned connections, what numerical thresholds did it actually use to make that classification?
That's a perfect way to frame the next level of understanding. In machine learning, when we talk about model weights, we're essentially talking about the brain or the internal learned structures of your trained model. They represent the numerical values, the learned rules, or the complex patterns that the model developed during its training process. These weights are precisely what the model then applies to new, incoming data to make its predictions or classifications. And BigQuery ML provides specific functions that allow you to, in certain cases, look inside and inspect these weights, offering a truly granular understanding of the model's guts.
So what do these model weights actually look like? I assume it varies quite significantly depending on the type of model we're using, right?
It absolutely varies. The term weights is a bit of a catch-all. For a simple linear regression model, the weights are exactly what you'd expect. The coefficients assigned to each input feature, plus an intercept term. These coefficients directly tell you the quantitative impact of each feature on the prediction. For instance, a weight coefficient of $10,000 for the feature number of bedrooms means that, according to the model, each additional bedroom adds exactly that amount to the predicted house price, holding other factors constant. Now, for a decision tree, or random forest model, the weights aren't single numbers in the same way. Instead, they manifest as the specific if-then rules, or the splitting criteria learned at each node of the tree. An example rule learned by the model might be something like, if square footage 1500 and a number rooms 3, then predict price range equals high. Inspecting the model means looking at these learned rules.
Okay, so rules for trees, coefficients for linear models. What about something complex like a neural network?
Right. For a deep neural network, DNN, the weights are represented by vast, complex matrices of numbers. These numbers define the strength of the connections between the artificial neurons across its many layers. It's truly like trying to decipher the intricate wiring diagram of a very sophisticated electronic device. So yes, in BigQuery ML, model weights is a general term encompassing these diverse internal components that ultimately define the model's learned logic.
Okay, that makes sense. Why would we actually want to look at these internal weights, especially for the more complex models? Well, what's the practical benefit of this really deep dive into the model's brain? Isn't XAI enough?
That's a fair question. Inspecting model weights offers several profound benefits that can sometimes go beyond what standard XAI provides. First, it helps you understand the model's core behavior at a truly fundamental level. You get insights into how it's making its decisions internally, not just the final output or feature attributions. Second, it can help confirm or identify truly important features in a different way. By seeing which features have consistently high absolute weights in a linear model, or are used in splits high up in a decision tree, you can get another perspective on which inputs the model considers most crucial. Third, it can be invaluable for debugging and potentially improving performance. If your model isn't behaving as expected, a look at the internal weights or rules can sometimes reveal counterintuitive logic, or perhaps features that are being unexpectedly over or underweighted. This might suggest ways to refine your input data or even the model structure itself. And finally, it allows you to confirm or challenge your real-world intuition. You can verify if the model's learned rules or coefficients align with your existing domain knowledge about the problem, ensuring a degree of logical consistency and sanity checking the model.
Okay, that makes a lot of sense, especially the debugging and sanity checking aspects. So, how do we actually access these model weights in BigQuery ML? Are there specific SQL functions tailored for different model types?
Yes, BigQuery ML provides dedicated SQL functions designed to retrieve model-specific weights or internal structures for certain model types. The ML weights function is the primary one for linear and logistic regression models. It gives you those exact coefficients and the intercept we talked about. Interestingly, ML weights is also used for matrix factorization models, often used in recommendation systems, to uncover the learned latent factors or hidden characteristics that the model found for users and items. For k-means clustering models, there's ML centroids. This function allows you to inspect the coordinates of the center point of each cluster the model identified. These centroids effectively describe the typical characteristics of data points assigned to each cluster, giving you a way to interpret and label your segments. If you're using PCA, principal component analysis, for dimensionality reduction, ML principal components reveals the new combined features, the principal components, that capture the most variance in your original data. And ML principal component tinfo provides statistics on exactly how much variance each of these components explains. Lastly, for Ermiclist time series models, which are used for forecasting, ML Ironman coefficients provides the coefficients that describe the trend component of your time series forecast. This helps you understand the underlying patterns the model identified in your historical data to make its future predictions.
Okay, that sounds pretty comprehensive for a good range of common model types, linear, clustering, PCA, AREMA. But are there any significant limitations? Are there popular model types where we can't directly see the weights using these straightforward SQL functions?
That's a crucial nuance, and yes, there are important limitations. BigQuery ML currently does not have direct SQL functions that allow you to retrieve the detailed internal weights or intricate structures for some of the more complex, often proprietary or highly nonlinear model types. This includes models like boosted tree, like XGBoost models trained in BQML, random forest, deep neural network, DNN, wide and deep models, or the AutoML tables models. Their internal complexity, the way they're stored, or sometimes their proprietary nature makes direct inspection via simple SQL commands impractical or impossible.
Oh, okay, so for those popular ones like boosted trees or DNNs, we're out of luck for seeing weights directly in SQL.
Directly in SQL, yes. However, for most of these unsupported model types, with one key exception, there's a powerful workaround. You can often export the trained model from BigQuery ML to Google Cloud Storage in a standard format like TensorFlow Save Model or ONNX. Once that model is exported, you can then load it into external machine learning libraries like the native XGBoost library or TensorFlow or PyTorch, perhaps in a Python or R environment. From there, you can use the inspection capabilities provided by those external libraries to examine the model's internal structure, feature importances, or weights in detail. So it requires an extra step outside BigQuery, but the information is often accessible. The one notable exception here is AutoML tables models. These are designed by Google to be more of a managed black box service focused on ease of use and high performance. As part of that design philosophy, Google does not currently provide a method to inspect their internal weights or exact architecture. You rely more on XAI for understanding AutoML models. So if we connect this to the bigger picture, accessing model weights where possible is like getting that peek behind the curtain of your machine learning models. It provides a deeper, more granular understanding of the underlying logic developed by your ML model during training. And this deeper understanding is often essential for effective management, thorough debugging, and ultimately building profound trust and confidence in your AI systems.
Okay, so we've really covered the full life cycle now. Building, optimizing, evaluating, using for inference, and even understanding the inner workings and explanations. But once a model is successfully deployed and working, the job isn't really over, is it? Especially in a dynamic business environment. Imagine you're running that high-volume bakery we talked about. You don't just bake one perfect batch of cookies and call it a day. You have a continuous process, right? A series of interconnected, repeatable steps. Mixing ingredients precisely, shaping the dough consistently, baking at the right temp, cooling, maybe decorating and packaging. To ensure consistent quality day after day and efficient production, you automate these steps as much as possible and ensure they flow smoothly from one station to the next. You build an assembly line.
That's precisely the concept behind an ML pipeline in the world of machine learning and MLOps, machine learning operations. It's essentially an automated, step-by-step workflow for orchestrating the entire life cycle of your ML models. Building, training, evaluating, deploying, maybe even monitoring and retraining. Instead of a data scientist or engineer manually running each individual step, like running a script for data cleaning, then another for model training, then another for evaluation, then another for deployment, a pipeline connects all these steps into a continuous, repeatable, and often automated process. Each distinct step within an ML pipeline is typically called a pipeline task or component. It functions exactly like a dedicated station on your bakery's assembly line, performing a specific, well-defined job before passing the work product to the next station.
Okay, that makes intuitive sense. But why go through the effort of setting up these automated pipelines? What are the significant tangible benefits for ML operations in practice? Why not just stick with manual scripts?
Oh, the benefits are truly transformative, especially for any serious production-grade ML initiative. First, sheer automation. It drastically reduces the amount of manual effort required, which not only saves time, but also minimizes the risk of human error, ensuring consistency every time the pipeline runs. Second, reproducibility. Your entire model building and deployment process can be rebuilt and redeployed consistently just by rerunning the pipeline. This is absolutely critical for debugging issues, for auditing purposes, and for ensuring that future versions of your model produce comparable and reliable results. Third, monitoring pipelines make it much easier to integrate steps for tracking the performance of your models over time and quickly identifying any degradation or triggering retraining when necessary. Fourth, scalability. Pipelines enable you to handle larger data sets and more complex models as your needs inevitably grow without requiring a proportional increase in manual overhead. The automation handles the scale. And finally, collaboration. Pipelines provide a structured, often version-controlled way for multiple team members, data scientists, ML engineers, data engineers, to work together efficiently on complex ML projects with clear separation of concerns for each task.
Okay, the case for pipelines is compelling for any robust production-grade ML environment. How does BigQuery ML specifically help us construct these automated workflows? What tools are available within the Google Cloud ecosystem?
Right. BigQuery ML integrates with or directly supports three primary tools or approaches for building these automated ML pipelines, each suited for different levels of complexity, flexibility, and integration needs. First, at the high end, we have Vertex AI pipelines. I often describe this as the advanced, highly customizable assembly line in a large factory. This is Google Cloud's premier dedicated service for orchestrating complex, flexible ML workflows across various services. You define your pipeline visually or programmatically as a directed acyclic graph. DAG. Essentially a flowchart where each box represents a distinct pipeline task and the arrows dictate the sequence of operations and data flow. Each task typically runs in its own isolated container environment, which ensures consistency and portability. Vertex AI provides a library of pre-built components specifically designed for interacting with BigQuery ML components for training a BQML model, evaluating it, running batch predictions, deploying it, etc. You simply wire these components together to build your end-to-end workflow. This approach is definitely best suited for large, complex, or highly customized ML projects that demand maximum flexibility, reusability of components, and robust MLOps capabilities that might span across the entire Google Cloud ecosystem, not just BigQuery.
Okay, so Vertex AI pipelines for the really sophisticated, potentially cross-service operations. What if the workflow is simpler, perhaps staying entirely within BigQuery for most steps?
For less complex or perhaps purely SQL-centric scenarios, you can often use Google SQL queries themselves, leveraging BigQuery's built-in procedural language features. Think of this approach as your simple recipe card, where you just list a series of sequential SQL steps. BigQuery's procedural language allows you to write multi-statement queries. You can execute different SQL commands sequentially, like create model, then ML evaluate, then ML predict. You can even incorporate basic programming logic like if statements, while loops, variables, and error handling to control the flow of execution within a single script. You can then save these multi-statement SQL scripts and schedule them to run automatically using BigQuery's built-in scheduling capabilities. This approach is ideal for straightforward ML pipelines where most, if not all, of the steps, like data preparation, model training, and basic inference, can be performed using SQL directly within BigQuery. It's excellent for rapid automation of relatively simple workflows without leaving the BigQuery environment.
Simple and contained.
Yep.
Got it. And the third option you mentioned was data form. How does that fit in?
Right, data form. I like to think of data form as the meticulously organized, version-controlled recipe book. Imagine a professional kitchen's recipe book where every single change to a recipe is tracked, rigorously tested, and can be easily rolled back if something goes wrong. It's built for team collaboration and reliability. Dataform is a service within Google Cloud, now integrated with BigQuery, specifically designed for developing, testing, version controlling, and scheduling SQL workflows, primarily for data transformation, EALLLC. However, its powerful capabilities for managing complex SQL dependencies and providing robust version control extend naturally to orchestrating ML pipelines where your tasks are predominantly SQL-based. Its key advantage over simple procedural SQL scripts is its strong emphasis on version control, integrating with Git and testing. Every change to your SQL code, including your create model or ML predict statements, is tracked, making collaboration seamless, auditing straightforward, and allowing you to easily revert to previous known good versions of your pipeline if needed. This makes Dataform ideal for more complex SQL-based ML pipelines that require robust version control, automated testing frameworks, and strong collaboration features for managing both the data preparation steps and the ML model lifecycle steps defined in SQL. So these three tools, Vertex AI pipelines, procedural Google SQL, and Dataform, collectively transform what might otherwise be ad hoc, manual ML processes into robust, repeatable, and scalable operations. They are absolutely instrumental in ensuring that your models are not just built effectively once, but are consistently updated, monitored, and performing optimally in a dynamic, real-world production environment. It's about moving from experimentation to reliable operation.
Okay, so we've built our automated pipeline, our model is running, maybe getting retrained automatically. We're done, right? Smooth sailing from here. But let's go back to that bakery analogy one last time. You've put your delicious, award-winning cookie recipe into full production on the assembly line. Customers love it. But what happens over time? Maybe your main flour supplier changes their milling process slightly. Maybe the ambient temperature in the bakery fluctuates seasonally, affecting the ovens. If you don't continually taste test your cookies, check the quality of incoming ingredients, and monitor your oven temperatures, the quality and consistency of your final product could degrade slowly, subtly, without you even realizing it until customers start complaining.
That's a perfect analogy, and it highlights exactly why we need BigQuery ML model monitoring. It's the essential practice of regularly, systematically assessing your deployed machine learning models to ensure they continue to perform well and accurately in the real world long after they've been initially deployed. Specifically, model monitoring typically involves systematically comparing the statistical characteristics of the data your model was originally trained on with the characteristics of the data it's actually encountering in production, what we call the serving data.
Okay, but why is this monitoring so profoundly crucial? If we train the model well and evaluate it thoroughly, can't we just assume it will keep doing its job reasonably well indefinitely?
Unfortunately, no. That's a dangerous assumption in the real world. The reality is that machine learning models perform best, often only perform well, when the data they make predictions on is statistically similar to the data they originally learned from during training. If the real-world data begins to shift or drift over time, and it almost always does in some way, your model's accuracy and reliability will likely degrade, sometimes quite rapidly, even if the model's code or weights haven't changed at all. This phenomenon is often called model performance deterioration or model staleness, and it's a very common and significant challenge in operationalizing machine learning, MLOps. Monitoring helps us catch two primary categories of data issues that cause this degradation. First, there's data skew, sometimes called training serving skew. This refers to significant systematic differences between the statistical properties of your training data and the serving data that the model encounters in production right from the start or soon after deployment. Using your flower example, it's like training your robot flower identifier exclusively on professionally photographed, vibrant, perfectly fresh garden roses under ideal lighting conditions.
The perfect training set.
Exactly, but then deploying it to identify roses from blurry cell phone pictures taken indoors, maybe of slightly wilted flowers or different, rarer varieties. The disparity between what it learned, perfect roses, and what it sees in production, real-world roses, can cause major errors. Skew means the training reality doesn't match the serving reality.
Okay, that's skew. What was the second one?
The second is data drift. This refers to changes in the statistical properties of the serving data itself over time. This is a dynamic shift that happens after the model has been deployed. Think back to your rose supplier. Maybe over the course of a year, due to changing seasons or suppliers, they gradually start sending you roses that are, on average, less fresh. Or perhaps subtly different varieties start becoming more common. Your model, which was trained on the characteristics of the roses from last year, might start to struggle with these evolving input characteristics. That's drift. The world changed after the model was trained. By detecting these skew and drift issues early through continuous monitoring, you can proactively take corrective action. Usually, this involves retraining your model with new, more recent and relevant data, or perhaps adjusting features. This ensures your model remains smart and relevant in a constantly changing world rather than becoming quietly obsolete.
Okay, detecting skew and drift is clearly vital. How does BigQuery ML specifically help us do this? Are there dedicated SQL functions for monitoring these phenomena?
Yes, BigQuery ML provides several powerful SQL functions specifically designed for data monitoring and validation. First, there's ML Describe data. This gives you basic descriptive statistics for any data set, things like counts, null counts, averages, standard deviations, min-max values for numerical features, and top values frequencies for categorical features. It's excellent for getting a quick initial profile or nutrition label for your training data and then comparing it manually or programmatically to the profile of your serving data to spot obvious differences. For more automated skew detection, we use ML Validated Data Skew. This function is clever. It compares the statistics of your current serving data directly against the training data statistics that BigQuery ML automatically calculated and saved when your model was initially trained, using ML Training Gimfo. It's designed to automatically flag statistically significant, potentially anomalous differences based on predefined thresholds or statistical tests. So you're directly comparing your current production line flower statistics to the original recipe flower statistics to see if there's a significant mismatch.
And for drift, the changes over time.
Right. For tracking changes over time, drift, you use ML Validated Data Drift. This function works slightly differently. It compares the statistics of two different sets of serving data, for instance, comparing today's incoming data statistics against yesterday's data statistics, or maybe this month's data against last month's data. This helps you identify gradual changes or shifts in the data distribution itself over time. A particularly useful related function here is ML Feature Set to Time. If you're using BigQuery time travel or snapshots, this lets you retrieve the data statistics from a specific point in the past, allowing for very precise historical comparisons when using ML Validated Data Drift.
Okay, those sound useful for basic validation. Are there more advanced options if we need really granular monitoring or custom checks?
Absolutely. For situations requiring even more advanced, fine-grained statistical analysis or sophisticated comparisons, BigQuery ML offers deeper integration with TensorFlow data validation. TFDV. You can use functions like TFDV describe to generate detailed TFDV statistics protos, and TFDV validate to compare datasets against a predefined schema or against each other using TFDV's more extensive set of validation checks. This gives you a much more rigorous and customizable comparison framework, akin to getting a full chemical breakdown and quality control report for your ingredients, rather than just the basic nutrition labels. This is particularly useful if you need to integrate BigQuery ML monitoring with existing enterprise monitoring solutions or have very specific custom validation rules you need to enforce.
Got it. So how do practitioners typically implement this in the real world? And crucially, can this monitoring be automated so we're not constantly running these checks manually? We need continuous vigilance, right?
Exactly. In practice, monitoring strategies often involve a layered approach using a mix of these tools. Basic monitoring might involve scheduled queries running ML-described data for quick daily or weekly health checks. Then, perhaps ML-validated data skew or ML-validated data drift runs automatically on a regular schedule, example daily, to detect anomalies based on statistical thresholds. If these automated checks flag significant skew or drift, that might trigger an alert for a human analyst to perform a deeper investigation, potentially using the more detailed ML-TFDV validate functions or other diagnostic tools. And yes, automation is absolutely key. BigQuery ML monitoring capabilities integrate nicely with Vertex AI model monitoring. This service provides powerful visualization tools, allowing you to see monitoring results, like drift scores over time, in charts and dashboards, making it much easier to spot trends and anomalies visually. And most importantly, you can set up scheduled queries directly within BigQuery to run your chosen monitoring SQL functions, ML-validated data skew, ML-validated data drift, etc., automatically at regular intervals, hourly, daily, weekly. You can even configure these scheduled jobs to send email notifications, publish messages to PubSub, or trigger cloud functions if data skew or drift is detected beyond a specified threshold. This prompts immediate investigation and can even automatically trigger a pipeline to retrain the model if necessary. This really brings us back to that critical operational question. How do we ensure our supposedly smart systems remain intelligent and effective in a constantly evolving real world? Model monitoring isn't just a nice-to-have, it's the proactive, indispensable step required to maintain high performance, ensure reliability, and guarantee that your models adapt to changing realities rather than becoming silently inaccurate and potentially harmful.
Okay, we've covered building, optimizing, evaluating, deploying, explaining, automating with pipelines, and even continuously monitoring our models. It feels like we've covered the whole life cycle. But in a complex organization, you might end up with potentially dozens, maybe hundreds of these models floating around. Some built in BigQuery ML, maybe others imported, some simple, some complex. Managing them all effectively across their entire life cycle could become a real challenge, right? Imagine you're the executive chef running a large hotel kitchen. You have dozens, maybe hundreds of specialized recipes. Some you developed yourself in-house, like BigQuery ML models. Others you sourced from external culinary experts, imported models. Instead of having these recipes scattered across different notebooks, computer files, and binders, you'd want one central, organized digital recipe book, a command center, where you can easily find any recipe, see its history, compare versions, understand its ingredients, and quickly deploy it to the right cooking station for consistent preparation.
That's a perfect analogy for the role played by Vertex AI Model Registry. It serves as exactly that central, unified repository, that command center for all your machine learning models across the Google Cloud Platform. Crucially, it allows you to register your BigQuery ML models directly within this central registry, providing a single source of truth and a consolidated platform for managing them, right alongside any models you might have trained using other Google Cloud ML services, like Vertex AI training, or even models developed using external frameworks and then imported.
Okay, so consolidation is one benefit, but why else would you specifically want to go through the process of registering your BigQuery ML models in Vertex AI? What are the practical, concrete benefits for model management and MLOps?
Oh, the advantages are pretty significant for establishing robust MLOps practices. First, as you said, centralized management. All your model recipes, whether they originated in BigQuery ML, Vertex AI, or elsewhere, are discoverable, searchable, and manageable in one single pane of glass. This drastically streamlines operations and governance. It's like having that one universal remote or app to control all your smart home devices rather than needing a dozen different apps. Second, you gain robust version control specifically for your models. Just like a recipe might evolve over time, version 1.0 Original, version 1.1, less sugar, version 1.2, gluten-free option. The model registry allows you to explicitly track, manage, and compare different versions of your trained models. This is absolutely critical for audited purposes, for understanding performance changes over time, for A/B testing different model versions, and for easily rolling back to a previous stable version if a newly trained one performs poorly in production.
That versioning sounds critical for production systems.
It really is. Third, registration enables streamlined deployment, particularly for online prediction. Once a model, including a BigQuery ML model, is registered in Vertex AI, you can easily deploy it with just a few clicks or commands to create a Vertex AI endpoint, that scalable, low-latency prediction service we talked about earlier. The registry handles much of the complexity of packaging and configuring the serving infrastructure for you. It's like having a dedicated, always-ready production line for each approved recipe, ready to churn out cookies on demand without complex setup each time. And finally, registering your models with Vertex AI unlocks access to its broader suite of integrated MLOps capabilities. Once registered, you can more easily leverage Vertex AI's tools for things like advanced model evaluation comparisons across versions, more sophisticated continuous monitoring setups, and potentially more advanced explainable AI, XAI features and visualizations, providing a truly holistic view of your model's health and performance throughout its entire lifecycle.
Okay, the benefits seem clear for organizing and operationalizing models effectively. How do you actually go about registering a BigQuery ML model with Vertex AI? Is it complicated?
Actually, it's designed to be pretty straightforward. You have a couple of primary methods. Perhaps the easiest is the born registered approach. When you initially run your create model statement in BigQuery ML to train the model, you can directly include specific options right there in the SQL. You add model registry, Vertex AI, and you also specify a unique Vertex AI modeled, which will be the name of the model in the registry. This is akin to writing add to central recipe book under name, my famous chocolate chip cookies, right on the recipe card as you first develop it. Once the BigQuery ML training job completes successfully, the model automatically appears in the Vertex AI model registry with that ID, usually as version 1.
Simple enough if you plan ahead. What if you have an existing BigQuery ML model that wasn't registered when it was created? Can you add it to the book later?
Yes, absolutely. If you have an existing BigQuery ML model that wasn't registered at creation time, you can add it to the Vertex AI model registry afterwards. This can be done quite conveniently through the Google Cloud Console UI. There's usually an option on the BigQuery ML model details page. Alternatively, you can do it programmatically using an alter model let set options, Vertex AI modeled, SQL statement, or via the BQ command line tool, or using the BigQuery client libraries APIs. It's like finding that valuable old family recipe written on a stained napkin and deciding to formally transcribe it and add it to your meticulously organized digital recipe book.
Good to know you can do it retroactively. Now, how does Vertex AI handle different versions if you retrain or update a model that's already registered?
That's a core strength of the model registry concept. When you first register a BigQuery ML model with a specific, unique Vertex AI modeled, it's typically recorded in the registry as version 1, or you can assign a specific version alias. If you later create or update another BigQuery ML model, maybe through retraining with new data or different hyperparameters, and you register it using the exact same Vertex model modeled, Vertex AI automatically recognizes this and treats it as a new version of that existing model. For example, it becomes version 2, then version 3, and so on. It maintains a clean historical record of your model's evolution under that single ID. However, there's one crucial warning here. Be very careful with the create or replace model syntax in BigQuery ML. If you use create or replace model with a BigQuery ML model name that is already associated with a registered model ID in Vertex AI, the or replace part will actually delete the existing versions in the model registry associated with that ID and replace it entirely with the new model as version 1 again. You lose the history. So if you want to maintain version history, use create model with the same Vertex AI modeled for new versions. Don't use create or replace model on a registered model unless you intend to overwrite.
Oh, that's a very important distinction. Watch out for create or replace. Okay, are there any other considerations, maybe regarding location or specific limitations when integrating BigQuery ML models with the Vertex AI registry?
Yes, a couple of points. Regarding location, if your BigQuery ML model resides in a BigQuery multi-region location, like US or EU, when you register it, it will be synced to a specific regional location within Vertex AI's infrastructure. For example, models in the US multi-region usually sync to the US Central 1 region in Vertex AI. Single-region BigQuery ML models just remain registered in their respective regions. This is usually handled automatically, but good to be aware of. As for limitations and deletion, To remove a BigQuery ML model entirely from the Vertex AI model registry, the process is simple. You just delete the model within BigQuery ML itself using drop model. This action automatically triggers its unregistration from Vertex AI. However, and this is another crucial prerequisite, if that registered model is currently deployed to an active endpoint in Vertex AI, meaning it's actively serving online predictions, you must undeploy it from that endpoint first before you can successfully drop the model in BigQuery ML. You can't just delete the master recipe if the kitchen is currently using it to bake cookies for a live party.
Right, stop the production line before removing the recipe.
Exactly. Also remember that you cannot register remote models in Vertex AI because they are, by definition, already just pointers to models that exist in Vertex AI. And finally, some specific BigQuery ML model types, while they can be registered in the Vertex AI model registry, like imported TensorFlow or XGBoost models or even Arima Plus models, they cannot always be directly deployed to a Vertex AI endpoint for online prediction using the standard built-in containers. They might require you to provide a custom serving container or use alternative deployment methods if you need low latency online serving for those specific types registered from BQML. Native BQML models like linear regression or DNNs usually deploy more easily. If we connect this to the bigger picture one last time, this seamless integration between BigQuery ML and the Vertex AI model registry truly transforms your capabilities. It elevates your work from just training models within BigQuery to establishing a powerful, centralized platform for managing the entire end-to-end lifecycle of your machine learning assets. It's about moving beyond just building models to achieving robust, scalable, and governable machine learning operations. Hashtag tag outro.
And that really brings us to the culmination of our deep dive into the world of BigQuery ML. Wow, we covered a lot of ground there. We've journeyed right from the beginning, understanding how you can build sophisticated machine learning models using the familiar power of SQL, all the way through rigorously optimizing them with automated hyperparameter tuning, evaluating their real-world performance, putting them to work with versatile batch and online inference options, then understanding the why behind their predictions, using explainable AI, even peeking inside their learned logic with model weights where possible, and finally, managing them efficiently and reliably at scale using automated ML pipelines and the central command center of the Vertex AI model registry. Our hope really is that this detailed exploration equips you with a powerful new lens, maybe some new tools in your toolkit to extract truly valuable, actionable insights from your data in ways you perhaps hadn't considered before.
Yeah, our aim throughout this deep dive was really to illustrate how BigQuery ML, especially when coupled with its robust surrounding ecosystem like Vertex AI, genuinely democratizes many complex machine learning tasks. It truly makes sophisticated, explainable, and production-ready machine learning significantly more accessible to a much wider audience: data analysts, SQL developers, data engineers, not just specialist data scientists. It empowers you to move more easily from raw data to impactful predictions, and to do so with greater ease, transparency, and the operational rigor needed for real-world deployment. So perhaps we can leave you, our listener, with this provocative thought to mull over for your own continued exploration. What seemingly intractable problem, maybe a prediction or automation task that seems too complex, currently sits hidden within your existing data that you could potentially tackle right now by teaching a computer to find patterns using the SQL skills you already possess, leveraging the power of BigQuery ML?
That's a great question to ponder. Think about the immense possibilities that BigQuery ML unlocks, removing some of those traditional barriers to entry for machine learning. We strongly encourage you to explore its capabilities further based on what we've discussed today. Thanks so much for joining us on this deep dive.